Alright, let's take a problem like this, in which this is ball or hockey puck A, this is hockey puck B, and the velocity of B initial, or 1, is going to be just 8I. Velocity of A at 1 being the initial, is minus 10I. Now what we have here is kind of interesting, because what we've got is a coordinate system that originates at the impact, in which the line of impact is right here, and we need to break this into a new coordinate system. Okay, now the way I approach these problems is in a rigorous way. I always have a systematic way of doing things. One of the things I see here is I see a coordinate system that's x. I see a coordinate system xy. Then I see one along the line of impact, which, for lack of anything better to say, would be R and S. Let's say you had base vectors that looked like this, I, J, and I'll call this base vector ER and this base vector ES. So if I were looking to break this down, I can tell you ER looks very familiar. ER runs up this line right here, and it looks to me like it's 3/5 of I plus 4/5 of J. So in other words, I'm just taking a vector that sits right here, and its length of 1, and I'm trying to find its coordinates in the x and y. So you'll see this is fairly common, and I have done this in class several times, so this shouldn't seem to be too unfamiliar to you. ES, on the other hand, points back in this direction. And so what you'll find out there is it's minus 4/5 I plus 3/5 J. And I can make that quick analysis, because if I do ES dotted with ER, I should end up with 0I plus 0J. And you'll notice that you have a 4/5 right here times a 3/5 on the I component. You should end up with 3/5. In other words, you'll end up with, well, anyway, that's a mistake right there. Let's forget that, because that's not true. It's just dot products are not going to be a vector, so scratch that. But in essence, what I'll have is 3/5 times minus 4/5 plus 4/5 times minus 3/5. So in essence, the 3/5 times the 4/5 here, plus this 4/5 times that 3/5 with the minus sign canceling them out, which that's going to be equal to 0. So all that, I'm trying to figure out how I can scratch it all out. There we go. That being the case, you could list this in this way. You could basically list them as a vector is equal to a matrix, which is 3/5 and 4/5 minus 4/5 and 3/5. Over here you'd have I and J. Now, what we really need here is we need to be able to express this in the terms of ER and ES. And so we need to be able to convert our velocities into this new coordinate system. Now, it just so happens that what I need to have is I need to have this equals to some matrix times ER and ES. Then I can replace this I right over here, replace this I right here with this row that comes out here. It doesn't erase that way. So that being the case, it turns out I can head off to MATLAB-like product, and you'll see I already typed this out. Let's see if I can draw it down. You'll see, okay, this is Scilab, by the way. Scilab, if you are not willing to pay for MATLAB and you're just using it at the lower level like what I'm doing here, it is very, very compatible to MATLAB. So what you'll see is I'm doing 3/5, then 4/5, and then the semicolon moves me to the next line, and I have minus 4/5 and 3/5 right here. You take the inverse of it, and you notice it's the transformation. The diagonal stayed the same, and then these swap signs. Now, it always ends up being that way if you're having a transformation. So, what I can simply write down is 3/5 minus 4/5, 4/5, and then 3/5. So now, if you notice, I can go in here and take this out and replace it over here with these. Or that statement should have been in reverse. But let's do that real quick. What I'll have is 8 and then 3/5 times 3/5. Then I'll have minus 8, and I should have made that something that was divisible or had 5 on it, then I would have gotten integers, but it's too late now. 8 times 4/5 here. Then I'll do the same thing here, but what happens, I have a minus sign in front of the 10. So what I end up with is minus 10 times 3/5, and then plus 10 times 4/5 there. So I have now the velocities in a new coordinate system, and what I'm going to do is move the page on down. And I'm going to say velocity of B initial is now equal to, okay, I'm going to go into Scilab and see if there's some simplification here. 4.8, okay, and then 6.4, okay. And then velocity A initial will be nothing more than, okay, and then 10 of that's 2, that's minus 6. So 10 divided by 5 gives me 2, times 3 gives me 6 ER. And then plus, same thing here, except I end up with a 4. 10 divided by 5 gives me 2, times 4 is 8 ES. And so now I have my coordinate systems set up so that I have oriented them in such a way that R is the line of impact, and I guess you could say S is not. So how about that? So now I need to jump off with this and say, well, I've got two ways that I can run through this. One is I can come through here and do the equation along the impact, and let's take a look at it. The velocity along the impact. Okay. And did I say the mass of these things? I did not. let's make this one, it's in red, so let's make this one 15. Let's make this one 10. Okay, so what I need to do is MA VA initial plus MB VB initial is equal to MA VB after impact plus MB VB after impact. Let's see if I can get rid of that. No, I gotta use the eraser. That is not right. It has to be A after impact. So mass A before, mass B before, mass A after, and mass B after. Now, it turns out that the impact equation is in the R direction. So let's go ahead and strip out these R components, and we will just simply deal with S afterwards. So here we go. A was the big one, right? A was the 15. So you got 15. Velocity A before. Is it a long? Yes, that's correct. Got to put a minus sign there. It looks funny if I do it this way. So we have to remember we're using the R components here. Okay, plus 10 and 4.8 equals to 15. I have no idea what this is. And then 10 plus I have no idea what that is. However, let's make a grandiose assumption here. We have a coefficient of restitution. Okay, so we put our velocities up here, and we put our velocities up here. We've got to have, since I have an A and a B, then I have an A and a B. Now I need to determine if it's before, after, after. And you can use that basketball example we did in class to get an idea. So let's just say it's 0.8. Now we do have the information before impact. So I can simply do this, and I guess for me to do this I better, so what I'm going to do is I'm going to take this part, multiply it over here on the right. What I'll get is 0.8 times VB1. Now this is a vector equation, so VB1 is 4.8 minus VA1. Now VA1 is minus 6 equals to VA2 minus VB2. Okay, so I can quickly... Okay, I paused the video and picked it back up because I noticed that I did a check and the audio was attached to the surface. So I hope this audio is a little bit better. So let's pick it up from here. So if you take a look at this, it appears as though we have two equations. Let's see if we can figure out the actual values here. Looks to me like here I need to, there's still going to be some bumping and noise that I'm making because I have the keyboard, a mouse, a pen, and a Surface tablet here, and I'm trying to move the video or the audio source as far away as possible, so you'll still hear some of that. Okay, so I'm going to look for this equation. Let's see, 0.8 times 4.8 plus what looks to be 6, and I end up with 8.64, which goes 8.64 is equal to VA2 minus VB2. Then what I'm going to do is I'm going to grab this and bring it down here underneath and say 15 VA2 plus 10 VB2 is equal to, I need to find out what that number is. So here I'm going to bring Scilab back up, sort of scoot it up under there. And 10 times 4.8 minus 15 times 6 minus 42 is what I get. So here, minus 42. Now I could sort of cast this if I wanted to in a matrix. Since I have Scilab here, which is kind of like a MATLAB product, I can basically get it ready to do a matrix, but I need to express it in a matrix form. 1 minus 1 VA2 VB2 equals to, okay, if I got 1, so I'm rotating each side, but you can see what I'm doing here. 8.64 minus 42. Then I need to put 15 and 10. Okay, so if you're looking at that, I should be able to just knock that out relatively quickly in the Scilab thing. So let's do that real quick here, so that I have them up on the screen. Do a clear, and then I'll do inverse of a matrix, which is 1 minus 1, 15, 10. Okay, going to invert that matrix times what would appear to be 8.64 and minus 42. Looks a little bit funny, but I think it's okay. Okay, let's see if I can copy this down. Okay, I have to remember I may have to bounce back and forth. 1.77, okay, VA2, 1.776 minus 6.864. Oh gosh, it's going to be hard to remember. 6.864. Now there are other digits here that Scilab does the same thing as MATLAB in that it just doesn't show them unless you do a format long. But I'm going to stick with this. So let's go ahead and recap now where we are. Okay, so these particular values are only, here I use a highlight, are only available or solved in the R direction. So I need to write this down, that the VA2 in a vector form is 1.776 ER plus something times ES, and likewise VB2 is equal to minus 6.864 ER plus something in the S. Now, since there were no impacts along the S direction, there's no momentum to exchange, there's nothing going on there, you simply copy those down. So I will go in here and take this value and this value. Now I've got them listed A or B first and then A. So for A, I got to take a 8 down there. Oh, I wanted to switch pins. And for B, I want to take a minus 6.4. Okay, minus 6.4, which might as well get rid of that. Okay, so this is the velocity after impact. Now you could go do a variety of things, but this is essentially it. One of the things you might want to do is you might want to convert this back to your I and J, i.e. the X and Y coordinates. How do you do this? Well, it turns out something interesting here, and we'll do it, but we have to do it fairly slow because I don't want it to get too difficult. If I have, and what I'll do is I'll go copy these. If I have a set of equations that will in fact convert, oops, let me go ahead and get rid of, touch that red right there and get rid of it. Go away, there we go. If I go in here and I select this, do a Control C, drop down the page, and then put myself anywhere, say right there, Control V, I'll have this set right here. Now, if you take a look at this, what you'll notice is I can actually, oops, sorry about that, I copied the wrong one. Let's do that again. Here, we'll erase it. Okay. Go back up. Copy this one. Control C. Move down the page. Just take it, put it, say, right there. Now I can move it wherever. Okay, now what I'm looking at, let me go back to this and say, okay, now I can tell you that I can take, for ER, I can take this row times that and come up with an equation. And let's do that real quick. And if we do, we're going to notice something interesting here. So therefore, let's work on just A first. 1.776 times what is essentially 3/5 I and then 4/5 J. But that's this component. I need to also say 8 times ES, which is minus 4/5 I plus 8 times 3/5 of J. And let's stare at this for a minute. It's kind of an interesting set here. I would contend that what we just did is a matrix vector multiplication, but it wasn't the one that we thought of. Okay, let me show you what we're doing here. After, of course, I put parentheses around things. So if you look at it, I'm okay, again, let me recap so that we see this. I'm taking the value of ER from this equation. This row times IJ. And then I take the ES from right here. This row times IJ. I fill the first one out here. I fill the second one out here. Why? Because the second one is associated with this. The first one was associated with this term. If that makes sense to you, you're doing good. But let me get the yellow markings off this and I'll keep going. However, I contend that this is the same equation. Well, let me complete this first. I'll take this and this one put together, and I'll say VA2 equal to, and I guess I'll just bring up this, and I'll try, let me see if I can move this down the page so I can work this out a little bit better. CLC to clear the screen. 1.776 times 3 divided by 5 minus 4 divided by 5 times 8 gives me 5.3344. And if I'm not mistaken, it was a minus. And that is I. And plus, let's take a look at this. Clear the screen as well. And what I'll do is I'm filling out the J's, which the J's are 1.776 times 4 divided by 5 plus 8 times 3 divided by 5 gives me 6.2208. 6.2208, or wait, 2208, that's great. Now I can rest and say, okay, I'm done, but let's take a look at one thing here. Now, I copied something a minute ago. I'm going to go through the process of copying it and showing what I believe we're actually doing. And this is going to be back to where I am going to do. Sorry about that. That's the pause button. Okay, so we're back up here. I have the lasso, and I'm going to lasso the other equation. And here's what I'm going to lasso, and we're going to look at and do a Control C. I'm going to slide it down here. Just pop myself somewhere and do a Control V. And I'm going to move it, and I'm going to observe something here. Okay. First, let me erase my little chicken scratches there. But what I'm going to do is interesting. I hope this works out. But what I'm going to do is I'm going to come back, and I'm going to erase this, and I'm going to erase that. But before I do, let's go. Oops. Wait a minute. Okay. Let's. I think I can do this. Okay. Let's see. Okay, so let's look back at what I had here. What I had was the base vector. Now, if you imagine that I have a base vector, there's no particular reason I can't slide this over. Here's what I mean by this. Take the lasso. I'm going to lasso this. I'm going to slide it over. Then I'm going to take this one and lasso it, slide it over. And now I'm going to come in here and I'm going to say, hey, I'm going to make it in, I wish I could make it in some other color, but here, we'll make it in red. And I'm going to show you what I'm going to grab. I'm working on VA, right? And so what I'm going to do is I'm going to grab the components of VA, this one, and this one, and I'm going to stick them right back in here. And watch what happens. 1.776 and 8. So what will go right here will be VA to X, VA to Y. Now let's see what happens to this. Now I can't very well enter the base vectors, but I know if I multiply that base vector times 1.776, I get this. So it's implied that these base vectors are sitting in this vector right here. So let's slide this down, go up and take Scilab, and let's take a look at this. Now, I'm not sure what I have anymore, so I'm going to take this vector, this matrix here, sorry. Let's do a clear again. And now I'm going to do, here I'll even do a clear here to get rid of everything. And then say, well, K is equal to 3/5 minus 4/5. Next row, 4/5 and 3/5. Oops. Okay. Here, I'm going to have to slide this up the screen. What I did is I didn't put the bracket on the left. So there's my matrix. Okay, Looks pretty much like that's what it is. Now I'm going to take the right hand side. So now that I have this, here, let's do this so I can see it all. So here's my matrix. In fact, that's the 0.6, which sits right here, minus 0.8, which sits up here, 0.8, which sits down here, and then 0.6, which sits right there. Now I'm going to take this one, create that, call it a matrix or a vector B equal to 1.776 and 8. Oh, I did it again. Now there's my vector on the right hand side. So okay, let me catch myself in it, and I'm going to do a clear so I can just look at the B. So there's my B. This is the same value as that. So what I'm going to do is multiply K times B. K times B, capital K times B, equals to, and let's take a real close look at what this is. Minus 5.3344, which sits right here, and 6.2208, which sits right here. So often you can use this transformation to determine these values pretty quickly. I can, using this same method, which by the way, this matrix is uniform in this, these values are the components. So if I grab the components, say, not of this one, but of these two, I'll get VB. So I can just simply go down and write that. Velocity of B final will be equal to, well, let's see. I can do it in a component form, which would be, okay. Get rid of, I think I could do that. I'm going to get rid of that. Okay. Which will be in component form looking like this. 3/5. Okay. 3/5 minus 4/5. 4/5 and then 3/5 times, grabbing the components, would be minus 6.864 ER. Minus 6.4 ES. Looking at it from that perspective, I should get, and let's slide this up, go back. Now I'm going to multiply, do this, clear, K times a vector which has minus 6.864 and then minus 6.4 for the second entry. Means I get a 1 and a 1.0016 1.0016 I and minus 9.3312 J. So there's my answer for the second one. Alright, so I think we could claim that this problem is finished. We could look at a vector diagram of what this looks like after the impact. If we wanted to, I guess we could. You know, we knew they came in like this and like that. But now, if we look at them, VB2 looks like it goes to the right 1, roughly, and down 9. So it's quite a bit like this. So after impact, the one that came from the left, which was the B, turned and went down. So this is VB2, whereas before impact it was like this. Okay, the other one, which before impact was like this, after impact it looks like it's to the left 5 and up 6. So it looks like it heads off in that direction. So here was the before, and there was the after. Here was the before, and there was the after. You could make several comments about that, or directions, or find angles and stuff. But for me, I think it's easy for me to draw this in a vector sense, and it's easy for me to draw that in a vector sense, and we'll just leave it at that, and we'll say we're done here.